Welcome to this first training video of the eGHOST project. This video aims to present to you the eco-design methodology that has been developed within the framework of the project for hydrogen systems. First of all, you will have a first overview of the eGHOST project objectives, and then the eGHOST approach for eco-design hydrogen systems will be presented to you. The eGHOST project is a European project funded from the Fuel Cell and Hydrogen Joint Undertaking in 2020 under the Co-Development of Eco-Design Guidelines for Fuel Cell and Hydrogen Products. The project started in 2021 and ended in 2024. The objective of the project was first of all to develop fuel cell and hydrogen eco-design methodology, then to contribute to European initiatives related to sustainability of hydrogen systems, and finally to formulate some eco-design guidelines for fuel cell and hydrogen products. Two case studies were done during the project. The first one was related to proton exchange membrane fuel cell technology, and the second one was related to the eco-design of solid oxide electrolysis technology. The coordinator of the project was the IMDA Energy Foundation in Spain, and the project involved 7 partners from research and technological organizations or industries, as well as academic partners. The eGHOST project is the first milestone in the eco-design of fuel cell and hydrogen products. It aims to provide robust eco-design guidelines for this kind of products at different levels of development, from the early design phase to the final definition of the product. And as you can see on the figure, a specific eco-design methodology has been developed within the project using life cycle assessment approach, social life cycle assessment, and life cycle costing in order to define eco-design ideas and improve the sustainability of 2 case studies, a PEMFC stack and a solid oxide electrolysis cell stack. The eGHOST approach to develop eco-design guidelines for the 2 case studies were done in 4 steps. The first step was the first sustainability evaluation of the case studies, with the evaluation of the environmental, social, and economical hotspots for 2 stacks, the PEMFC and the SOSC. Once the sustainability hotspot has been defined, first eco-design ideas were generated for the 2 case studies, and these eco-design ideas were really related to the different sustainability hotspots that have been found. Based on these first eco-design guidelines, some new stacks product concepts were designed and defined by the consortium, integrating some eco-design aspects, and finally, a final sustainability evaluation of the eco-design products concept were realized for final guidelines validation. The first case study was the proton exchange membrane fuel cell. This is a technology mainly used in vehicles, and it's composed of membrane electrode assembly that are stacked together in order to use hydrogen to produce electricity in order to run the vehicles. The case study parameters are the following. The perimeter we have taken into consideration for the redesign of this case study and also for the life cycle sustainability assessment was only the stack. The size of the system was a 48 kilowatt stack, and the technology was a representative stack design that is currently available on the market. The application is a light commercial vehicle application, and the timeline is a current technology. The data used for the first sustainability evaluation of this case study was provided by Symbio France, mainly with a bill of material. As you can see here, a full bill of material was generated within the project in order to be able to collect the data necessary for life cycle assessment, social life cycle assessment, and also life cycle costing of the PMFC stack. You will find in the second video of this training the main results of this first sustainability evaluation for this case study. The second case study was a solid oxide electrolyzer stack. So the solid oxide electrolysis cell is a solid oxide fuel cell that will run in reverse mode in order to achieve the electrolysis of water at high temperature to produce hydrogen. The parameters taken within the framework of the eGHOST project for this case study was also the stack with a cradle to grave without the use phase. And the size of the system taken was a 5 kilowatts stack taken. The technology is a cathode-supported planar cell, and we use some prospective data to model a stack that will be currently developed at 2030. The number of cells for the stack were 26 cells, and the single repeat unit active area 100 centimeters squared. The single repeat unit total area was 144 centimeters squares. The data taken for the first sustainability evaluation was some literature data and also some partners' expertise. As you can see here, we have different parts composing the stack. We have the electrolyte, the cathode, the anode, the interconnectors, the anode and cathode mesh, the sealants, and the end plates. And the list of materials composing these different parts were done with their different quantity of materials related to each component. Regarding the prospective parameters of the solid oxide electrolyzer stack, we decided to take an electricity mix for the manufacturing of the stacks with a temporal horizon of 2030 in Spain. And as you can see here, you have the different repartition of the energy sources for this mix. And we have also some technical prospective parameters set for the first sustainability evaluation, with the definition of active area, a current density, a degradation rate, and also a lifetime rate. In this first step of the eGHOST methodology, we applied environmental life cycle assessment, social life cycle assessment, and life cycle costing to perform a first life cycle sustainability assessment of the two stacks. The main results of this life cycle sustainability assessment are presented in the second video of this training. Based on the hotspots found in the life cycle sustainability assessment of the two case studies, the eGHOST project organized some eco-design workshop with hydrogen actors to generate some eco-design ideas related to different life cycle phases of the different products. Some ideas were generated to help the selection of low-impact materials, to reduce the material usage inside the stacks, to optimize the product techniques, optimize the distribution systems, and reduce the impact during use. We had also worked on eco-design ideas to optimize the lifetime of the product and also the end of life of the systems. That means that we define some eco-design ideas to improve the recyclability of the stack, the demountability, and also the remanufacturing of the stack. It was the step 2 of the eGHOST methodology. You have here some ideas generation results example. So this is some eco-design ideas for the selection of low-impact materials for the PMFC stack. For example, you have some ideas related to the recycling of platinum in order to reduce the use of virgin platinum with recycled platinum that is already available on the market and that meets technical requirements. You have also some ideas related to the replacement of stainless steel by aluminium in order to reduce the stack weight. In total, more than 150 ideas were generated during this session and this workshop for both case studies, and the ideas were classified and refined in order to define some realistic short-term concepts of the stacks based on short-term action that will be realized and implemented in the near future, and medium to long-term concepts based on action that could be implemented in a further temporal horizon. The step 3 of the methodology was to develop new stack concepts integrating some eco-design ideas. For example, we had an optimistic product concept for the PEMFC stack with some implemented eco-design action, such as the use of recycled platinum, the reduction of platinum loading, the optimization of the triple phase boundaries, a mass reduction of the BPP and the ionomer, the refurbishment of BPP and the closed-loop ionomer recycling. The same approach has been defined for solid oxide electrolyzer stacks. We developed some life cycle inventories based on guidelines recommendation, and the main realistic and optimistic concepts were based on the reduction of the mass of materials used in the different layers of the stacks, the reduction of critical raw materials, and also the reduction of the use of the different steel for the end plate and interconnectors component. Finally, the step 4 of the eGHOST methodology aimed to perform a final life cycle sustainability evaluation of the product concepts, the realistic one and the optimistic one, in order to validate the eco-design ideas and also to build some eco-design guidelines for both technologies. So you can find the eco-design guidelines, the final one, on the eGHOST website. The first one is under deliverable 5.2. It's the eco-design guidelines for solid oxide electrolyzer. And the second one is deliverable 5.1, and it's eco-design guidelines for PEMFC technology. To conclude on this first part of the eGHOST training, we developed within the framework of this project an eco-design methodology for fuel cell and hydrogen systems. This methodology is done in 4 steps, and within the first sustainability evaluation of the 2 case studies, we were able to develop more than 150 eco-design ideas that led to the development of new stacks product concept for PEM fuel cell and solid oxide electrolyzers, and to validate final eco-design guidelines for both products. You can now go to the second training materials to check more detailed results on sustainability evaluation of the PEMFC and solid oxide electrolyzer, and also to get a detailed overview of what's inside the eco-design guidelines for both products. Thank you very much for attending this training, and see you in the next video.